In the previous video we have discussed two methods to reduce reflection of light at the front surface of a crystalline silicon solar cell. In this video we will show the third method to reduce reflection losses. We will look at the effect of parasitic absorption losses, and we will demonstrate an important role of the back metallization, namely to increase the path length of light in the device. The third method to minimize reflection is by texturing the wafer surface. Incident light that is reflected at a textured surface can be reflected at angles such that it is incident somewhere else on the surface, where it can still be coupled into the silicon wafer. The angle of 36 degrees is chosen intentionally, and we will see this in a short moment. When we introduce the atomic structure of crystalline silicon, we discuss the two most commonly used crystal orientations, 1, 1, 1 and 1, 0, 0. When we now look at the two-dimensional projection of the 1, 1, 1 and 1, 0, 0 surface, where the atoms are approximated as spheres, we can see that there is a difference in atomic density. This is what we call the packing density and can be calculated as the fraction of the area taken by the atoms. For the 1, 1, 1 orientation, this packing density is calculated to be pi over 2 times the square root of 3, which is around 91%. For the 1, 0, 0 orientation, the packing density is pi over 4, which is around 79%. If you are interested in how these packing densities are calculated, have a look at some literature on material studies of the face-centered cubic structure. Furthermore, each atom at a 1, 1, 1 surface is back bonded by 3 atoms, whereas for the 1, 0, 0 surface, each surface atom has 2 back bonded silicon atoms. This plays an important role in the texturing process of crystalline silicon wafers. We will now briefly go through the production process to obtain textured wafers, in which it becomes clear why we showed an angle of incidence of 36 degrees in the introduction figure. A surface texture on monocrystalline silicon wafers is obtained by using a strong alkaline solution and submerging the wafers for a set amount of time. The solution will etch away material such that it will get a dull appearance, resulting from a reduction in reflectivity of the surface. An acidic solution is used for multicrystalline silicon, as this will result in a more uniform etch rate across the grain boundaries. Multicrystalline silicon wafers are also commonly textured with a mechanical process or by lasering. We will now go back to actual profile obtained by wet etching of crystalline silicon. As the 100 plane of the lattice is less densely packed and has fewer back bonded atoms, the etching solution will attack the silicon atoms much faster in this direction than in the 111 direction. When a 100 oriented wafer is placed in the etching solution, eventually only the 111 surface will be exposed to the etching solution, and this results in a pyramidal texture that can be seen in this image taken by a scanning electron microscope, SEM. The angle of the 111 plane with the horizontal is around 54 degrees, which explains why we used 36 degrees in the ray tracing example as the angle of incidence between the light and the textured silicon. Note that this wedge etching method requires a very precise orientation of the silicon wafer, which makes it very effective for monocrystalline silicon. When we look closer at the surface morphology of the etched monocrystalline silicon, we observe different sizes of the pyramids and pyramids superimposed on others. This is called random texturing and is actually favorable for reducing the reflection. If the feature size of the pyramid is larger than the wavelength of the incident light, it will reflect multiple times on different faces, like we demonstrated with the ray tracing example. However, if the feature size of the pyramid is smaller than the wavelength of the incident light, it will serve as a gradual increase of the refractive index and hereby reduce refraction, as I explained in the previous video. Random texturing hereby reduces reflection over a wide range of wavelengths. In this slide you can see the effect of texturing on the appearance of a silicon wafer. A flat wafer, as shown on the left, appears shiny and acts nearly as a mirror. The random pyramidal texturing, as discussed, reduces the reflection considerably and the wafer looks dull, as you can see in the middle picture. Recently, more advanced texturing has been obtained by means of dry etching. In that case, the texture does not have a pyramidal shape, but needle-like pillars are obtained with high aspect ratio, and the wafer will appear black for the human eye, as none of the incident light will be reflected. This is shown on the right hand side. With so-called black silicon, the reflectance up to a wavelength of 1100 nanometers, corresponding to the bandgap of crystalline silicon, can be made virtually zero. The reflectance profile of polished, random pyramidal textured and blacks are shown here. When we add the reflectance curve of black silicon, we can conclude that here that texturing can reduce the front surface reflection almost completely. However, we must note that black silicon is in a research status and not available on the market as of today. Now that we have minimized reflection of light at the front surface, we will shortly talk about the parasitic absorption losses. These losses refer to light that is absorbed in layers that do not contribute to the generation of electron-hole pairs, and thus where no photovoltaic power is generated. One of the layers on top of the PV active layers is the silicon nitride passivation layer. The absorption curve of the material is shown here. We can clearly see that at short wavelengths some of the incident light is absorbed such that the external quantum efficiency of the solar cell is reduced in this wavelength range. We will now turn our focus towards the back of the solar cell, where light can be transmitted or absorbed at the back surface. When light has not been absorbed in the silicon wafer after passing through the bulk, part of the light might escape at the back surface. The most obvious solution to this problem would be to increase the thickness of the absorber layer. In fact, 1 millimeter of silicon will absorb virtually all the photons up to the bandgap of silicon. However, the maximum thickness of the wafer is limited by the diffusion length of electrons in p-type silicon, as these electrons need to travel from the point of generation all the way up to the front surface. It would not make sense to generate electron-hole pairs close to the back surface when these electrons will likely not reach the p-n junction at the front. Of course, material costs are higher if more material is used, but we neglect cost issues for now. Another strong argument to limit the thickness of the wafer has been discussed in the video on the open circuit voltage. The thinner the wafer base, the higher the open circuit voltage will be. Now, since the path length of light through the material is the issue, there are two other useful solutions. One method is to use a back reflector, which is in the standard crystalline silicon solar cell design, is present in the form of a fully metallized back contact. Other methods are using a material with a different refractive index, such that the light is internally reflected. The reflection at the metal back contact is roughly 90% for aluminium, such that it is equivalent to almost doubling the path length of light reaching the back of the solar cell. Combined with surface texturing, we can increase the path length even further, since light will be scattered and coupled into the device at an angle. Texturing the wafers is therefore also a useful tool to limit the thickness of the wafer while maintaining the short circuit current density and increasing the VOC. To summarize this video, we have shown that aside from the anti-reflective coating discussed in the previous video, the front surface reflection can be further reduced with texturing. This is at the same time a valuable addition to more than doubling the path length of light through the wafer in combination with a metal back reflector.